Okay. Let's get started with the CPS seminar. Let me introduce today's speaker. It's Professor Elisa Ferreira. Yeah, she will talk about cosmological tension and the statistical challenges in parameter inference. Okay, thank you.
Thank you. Thank you so much. First of all, I'd like to thank Pastor Kuhn for the invitation. I'm very glad to be here. And because when Professor Kuhn visited IPMU, we talked about already dark energy. I decided to talk about that. But then talking to you, all of you, I realized that none of you work on that. And maybe I should have chosen a more theoretical topic. But I still think I'm going to talk about some facts about observations that are interesting, even for our theories. Because after all, when we do our theories, we need to test them, right? So we need to have our foot in reality. And there is a huge amount of data coming in, very precise data, but also very problematic. So if there's something I'd like you to take from this talk today is don't fully trust the abstract of the observational papers you read. The communication between us theorists and the collaborations, it is really not as good as it should be. So then they use parameterizations like W0 W, which probably they should not, or they test this in this way or this way, which for us is like, why are you doing this? Like, this is maybe not the best thing you could be doing. And this causes problems in the results or even the interpretation of the results. That since we don't talk, we don't know, right? Since I have a theoretical background, but I wanted to test my models, in the past few years, I developed a little bit of this knowledge on the observations, enough to at least understand what they're doing. And maybe I could be a translator for you. So maybe take this as all the questions you can ask about the latest cosmological results that you wanted to know, but you had no one to ask. Second, I cheated a little bit. I wanted to talk about second topic. So it is kind of two talks. Let's see where we can go. But the second one, it is an even more fun curiosity, in my opinion, about the data that no one is talking about. And we theorists need to be aware so we can build the best theories we can choose. Another thing I wanted to say, I believe we're behind. I don't know how many times in history of physics theories were in front and then theory came and experiments came, or maybe experiments came and then theories came. My opinion nowadays is that we theorists are behind. There's a lot of data, a lot of tensions, a lot of things to be explained, and our models and our explanations are not up to the task. They are all degenerate with each other. They don't come from very good first principles. So it is important to listen to the observations a little bit. So sometimes let's stop and understand what they're saying so we can incorporate this in our theories. So like we were saying today in lunch, there was no reason to break parity in the universe unless someone goes and measures that, and then now your theories have to break parity. So listening to experiments is important. So that's why I feel like maybe it's a good talk, but I'll let you decide. Okay, so I'm going to talk about cosmological tensions today and how data analysis, analyzing this data could really make you conclude the wrong thing about your model or what the data is talking about. Before I start, let me advertise these two workshops that we're going to have at IPMU. This in November and this one in December. This one is about axions in Japan, everything, every aspect about axions, dark matter, axions, axion-like particles, or anything. We have an amazing list of speakers. And this one, dark matter and black holes, again, everything about black holes, primordial black holes, or the relationship with dark matter. Registrations are open, so please, we're close by, so I think you guys can come. All right, so let's talk a little bit about statistical methods in cosmology, because this is in the center stage for what we know about cosmology nowadays, right? So cosmology is a precision science, and it is indeed nowadays a precision science. We measure the parameters of the cosmological standard model with less than 1% precision. Some of them with less than 0.1% precision. But this owes much the progress on having these amazing data sets, but also much because of data analysis, right? So statistics. And how do you do statistics on large parameter spaces and large amounts of data, which is not easy. Again, we only have one universe, right? So you really have to squeeze statistical power out of your observations to be able to actually put good bounds. We don't have the LHC to just do the experiment many times. And with that, we constructed this beautiful lambda CDM model. Lambda, it is for dark energy, which explains the current acceleration of the expansion of the universe. And CDM is cold dark matter, which is our coarse-grained description of what dark matter is. It is not telling us anything about what dark matter is, but how it behaves. This is our current model, and we measure this very precisely with the data that we have. But to do that, to measure this so precisely with less than 1% precision, we have to analyze something like 30 to 40 parameters. How big is the size of the dish, or how big is the field of view, how well I understand dust. So a bunch of things that we're going to call systematics or instrumentation that you also have to fit to do the statistical analysis and also fit this to the data. So this beautiful data here, which is here is the power spectrum from CMB. This is the anisotropy in the temperature that we measure in the photons coming from the early universe. When I'm measuring this, when I'm fitting this, I'm not only fitting the cosmology, I'm fitting all these 30 to 40 weird parameters that also come into the analysis, which is very complicated.
So what is some of the examples of 25 nuisance?
Those are parameters. So for example, we need to subtract all the foregrounds, because when I'm looking at the CMB, there is dust in the middle, there is a bunch of things in the middle, so I have to subtract that. There's models, parametric ways of doing it. I also have to fit them. I have to fit what I'm measuring. So I'm measuring photons. I have a field of view of my telescope. How do I receive the photon? There's a bunch of those things that you have to, that enter this fit. And the data, it is informing us about those things as well. So when we show those beautiful contour plots, so for those who never saw, in those contour plots, we have the 2D, 1 sigma contour and 2 sigma contour. So the dark region here is 1 sigma, the lighter region is 2 sigma. And here is one parameter, here is another parameter. And this tells you what is the range of values that this parameter is given the statistical analysis. We always only show this beautiful one here, which is only the cosmology. But this should have 40 dimensions because we fit all the parameters.
Is there any room to increase the number of parameters?
Oh, yes. So here's where we're going. So the next decade, we all been hearing this, right? The precision is going to increase, the amount of data is going to increase. It's going to be the final gold area of cosmology. We never had the amount of data we'll have in the future with the precision we'll have. Yes, but this means with more precision comes more complexity of the data, more of those nuisance parameters. So I don't want to, maybe before in the CMB, because I was not so precise, I could ignore some effects that I didn't have precision to really see them. Now you can't. You have precision, you have to model everything well. So the next generation, especially of what we call large-scale structure surface, because we're measuring the position of galaxies in our universe. So this is a 3D. The CMB is almost 2D. This is a 3D distribution. Galaxies are different. They have their own morphology. They have everything. This amount of parameters is going to grow exponentially. So here is an example of one of those new probes. This is not even new. This is still the old one. And this is the amount of parameters we have. So this is something around also 30 something.
Are they very sensitive? these new.
That is the job of the person that is doing the analysis, to understand how sensitive they are and how much they can impact your analysis. Let's say I make a mistake on one of those parameters here, which have nothing to do with cosmology. It's just like the shape of my galaxy. And this affects completely my cosmological parameters.
So out of those 25, there are some that are very sensitive and some that are.
Yeah, so what we are seeing is that there's a lot that are very sensitive. So all of these ones are extremely sensitive. All of these ones are extremely sensitive. There is a tension nowadays that we call the assay tension, I'm going to explain, that can be completely debunked just by errors in those. What happened in the past is that we would only look to the cosmological parameters and we forget the others. Now I think we understand what we're doing. The precision is so good now that we're starting to realize that we're making small mistakes in the choices of how we analyze these parameters that are impacting completely the cosmological parameters and creating new tensions in the universe or solving tensions without solving. So although we all don't care too much about statistics, this is important. And we should know that this is important and this can affect.
Are you going to talk about other tensions?
Yes, I'm coming. So the question, which is important for all of us as a community, not only the people that do this because they are worried about other things as well, it is, are those effects important and how much they're important to the cosmology, the parameter inference of the cosmological parameters, that it is the goal of this. And this is going to be particularly important in tensions in cosmology. Because tensions, we're talking about things that are measured with precisions of 1%. So tiny errors here or there can have a big effect. So we need to minimize these effects as much as we can. So let's talk a little bit about tensions in cosmology. So what is the Hubble tension? And please ask questions at any moment. So Hubble parameter, which we call H0, it is one of the most important quantities in cosmology. It is the first quantity we measured in cosmology. It tells us the age of the universe, the size of the visible universe. It tells us almost every information we want to know about the universe. This is telling us what is the rate of expansion of the universe today. And giving this value, we know how old is the universe, how big is the visible universe, and many other quantities. This was the first quantity we tried to measure in cosmology. And as we were talking in lunch, we didn't know if this value was a 50 or 100. And we were super happy with this. We're amazing. We're measuring how fast the universe is expanding. This is amazing. Now this discrepancy, it is the 1% level. The discrepancy in the measurement of H0, it is between what we call indirect measurements and direct measurements. And the name says it all. Direct measurements are certain astrophysical observations where you infer directly the H0. So you're really measuring how fast this is going away from us. So you're measuring the H0, you're measuring a distance. And the indirect measurements, you're measuring some other quantity, like you're measuring this CMB anisotropies, for example, and you infer this quantity by assuming a cosmological model. So, Planck gives me this H0, assuming the Lambda-Zillian model. If I assume a different model, I have a different value. And remember that what I said, like this Planck, the CMB measurement, it is the most precise measurement we have in cosmology and astrophysics. There's nothing else that we measure as precise. So the indirect detection here gives us a small value, something like 67. And these indirect detections, in general, give you a large value. It is not all of them, and some of them have a big uncertainty. But the most precise of those measurements comes from the Schultz team, which measures the distance from supernova, what we call the distance ladder. So we're really using each object that is closer to us as a letter of something that we grow at more distance to us, to measure the distance to an object and infer H naught. And those values usually give a very high value. So something like the 2021 results give you something like 73. So if we compare this with the error bars that they have, which is what I call sigma, right? This is the errors. Think about a Gaussian and the error that we have in this Gaussian. This is the sigma. If I compare the distance of these two results, this is a 5 sigma tension. Yeah.
So it's a direct measurement. But as a theorist, I think we cannot help but assume that it's some theory, like general relativity works. I'm wondering what the higher theoretical background for that theoretical.
So I mean, we don't assume a cosmological model that could change this distance. We only assume things that could not change this distance. So for example, GR, we're assuming for everybody always, right? But this will be what I call a different model. So this will be, oh, I'm assuming a different model. But for those measurements, you don't have to assume anything. You're really just measuring the parallax of this. Then you're measuring the difference of brightness of this to this. So this is really direct. You don't have to assume a cosmological model. No. The other one you do. You have to assume GR, cosmological principle, lambda CDM, and then you infer it. And if you break one of those, you get
to make astrophysical assumptions.
You make astrophysical.
Blades, the supernovae.
Yeah.
You have to assume that they're standard candles.
Yeah.
There's a lot of
Exactly, and that's where I'm
dust coming.
coming. Yeah. What is the explanation for this? It could be systematics, which is what us cosmologists call the things we don't care, systematics, which is all the astrophysics. Oh, can I really compare the brightness of these two objects? Are they actually standard candles that I can actually compare them?
If
Or
you're not measuring anything.
Yeah, but if you're not measuring anything. Or is this new physics? Okay, the astrophysicists are doing a good job. Otherwise, why would they put like such a small bound, right? But it could be that you forgot something, or there's something we still don't understand in the how this type of star works, how this type of galaxy works. So there's these two explanations for the tension. Is it systematics, some astrophysics we forgot, or even some uncertainty that I underestimated? Or is it physics, new physics? This is really hinting on when we do the inference, we're using the wrong model. As you can see, not everybody agrees, right? We have here what we call the tip of the red giant, which is a different way of measuring distance. And they are also very precise, and they are right in the middle. The recent development on this, I can tell you, is that those two groups finally agree on the measurement of the distance to objects, perfectly agreement. But when they get the value of H naught, they disagree. Because one selects all the samples, the other one says, oh, these galaxies are bad, so I'm only going to use this ones. So I would say this is coming to a conclusion. A few years ago, they didn't even talk to each other, so we're getting there. Okay, so this is the Hubble tension. So one of these two explanations it is for this. And again, let me tell you, 5 sigma is discovering in particle physics. Okay? Of course, 5 sigma in cosmology is not the same thing because we have a bunch of, it's complicated, right? But it is pretty far away. It is something that you should be worried. It's not just a tiny hint. No. There's something here to be investigated seriously, right? So in this talk, we're going to assume that is new physics because after all, we're theorists and we cannot do anything about the systematics, right? So this is someone else's job. We just need to know that it could be it.
What's the bottom right part? Is it the average of the two data?
Oh, this one, yeah. So here's combining all the of everything. This is combining with Cepheids. This is combining with this one. Yeah, so different combinations of this data set to try to understand the tendency of those direct detections more towards higher values or not.
As combination of direct.
Of direct. And I think that's why people kind of think the tension is there, because those different things have completely different systematics. Those are completely different ways of measuring. So why are they all indicated large? H naught, we don't know. They need to prove their error bars, so we need to wait. So what can we do as theorists before that? We need to find theories that can explain this on this side, right? And I can already tell you we are maybe behind or for sure behind. Okay, so let me explain a little bit what I mean by indirect detection. So you can see how the cosmology enters. So for example, we're trying to measure the CMB. Again, the CMB is the first light we see from the universe. So the universe was really hot and dense. Photons, matter, everything was in this plasma. As it expanded, it cooled down and started getting bigger and bigger until the photons could just free stream and get to us. So we're seeing the universe in a very early time. And the anisotropies that we see in this temperature measurement actually tells us the anisotropies that we have in the universe at that very early time. So this tells us what is the seed of all the structures that we have in all this. And one of the best measured quantities in cosmology is what we call the angular scale at the sound horizon. Again, sound horizon is that moment where the photons started to free stream onto us. This quantity is actually measured with 0.03% precision, which is pretty cool. And it's pretty robust against all of those other things. You can really change these other parameters. This quantity is robust. So this is something we're sure we measure. And the definition of this, it is the sound horizon, the size of the sound horizon at this moment where the electrons free stream, divided by what we call the angular diameter distance, which is just this distance between. So here is us, and this sphere, it is the past around us. It is the sky we see in the past. And the definition of those quantities is A is the scale factor. So A today is 1. So it tells you time. So this is an integral from 0 to A star. And dA is an integral from 1 to A star. I have a backslash on that. So we measure this. This is what we measure. And then we want to understand what is RS and dA. So RS, let's put redshift. Redshift is a better quantity of time. So large redshift is early times, redshift 0 is today. So RS is a measure from the beginning of the universe until the last scattering surface. And dA is a measurement from the last scattering surface until today. So it's a late time measurement, and this is the early time measurement. Things that happen in the early universe. And this is, here we have the sound speed divided by h of z. Here's the Hubble parameter. So here you can see how the cosmological model enters. It enters here in this h of z that we put in this equation. But we're going to see that not only that. So I measured this, but the cosmology can change this to values of how they are. So there is what we call two solutions to the Hubble tension. What we call the late universe solutions, where we modify this part. So we modify this integral because this integral is late times. And there's the early universe solution, where we modify this part, which is the integral of the beginning of the universe into the last scattering surface. And the idea to solve the Hubble tension for the early universe solutions is that since this is fixed, I want to decrease this quantity here, make it smaller. Because this is fixed, I also have to decrease this quantity. And in order to do this, I have to increase h naught because this is divided. So it's very simple. We saw this and say, how do I make h naught bigger? I have to do a cosmology where I decrease this quantity and increase this one. Early universe solutions are known to be the ones that allow you to really do this change in cosmology, to change enough to solve the Hubble tension. Late universe solutions, there's so much data nowadays, and it's so well constrained that they're harder. It's harder for you to change the cosmology so much that you can actually solve the Hubble tension to the level that you need to solve the tension. So for that,
This question, if we look at the numerator is the early universe.
yeah, before recombination.
But what we need is the present power parameter.
Yes.
Right?
Yeah.
Which is in the denominator.
Yeah, but you can always write in some, because you decrease this one, but you have to decrease this one as,
Right.
yeah.
And maybe in the top of the numerator, by decreasing the sound
Yeah.
speed, we can reduce.
Yeah, I'm going to show this.
By the distance,
Yes.
horizon, the
Yeah.
power parameter, we can reduce in the new denominator.
Exactly. So anything you do here in the early universe that you have more freedom to do, because the data starts at recombination when this integral ends. So you have a lot of freedom in the data to modify here. It's going to affect the late time because this ratio needs to be constant. So anything you change here, you change this D, you change CS, you change H, anything you change here is going to change the late time because this has to be fixed. Yeah. So we're going to focus on the early time solutions because those are the best solutions. Those are the solutions that really do the job, or at least we think they do the job. So again, the idea, decrease RS because this decreases dA because this is fixed. This will lead to an increase on H of Z, H of 0. And how many ways we can do this? Before, we need to decrease this RS by something like 10 megaparsec, which may not mean anything, but it is, we know the value. To get that value close to that value, we know exactly how much we need to decrease RS. So this is a very phenomenological way of thinking. Then you come with your theory knowledge and you say, how can I make RS decrease by 10 megaparsec? I can alter a few things. I can change H of Z, right? So there's many ways of changing H of Z. I can add new components to the universe. I can say that there is new light degrees of freedom that I forgot. There is a new theory. Here, H of Z enters all the components of the universe, matter, radiation, dark energy, or any other things that you might want to have. You can change the recombination physics. You can say, oh, maybe recombination, this moment where the photons just free stream to us, happens in a different way. Maybe there's some interactions between the electrons and other things that we did not take into account that retards this in some way that changes this integral in the way we want.
Reduce the RS by 10. What is the value of the reference RS?
Sorry,
Could you explain the reference value of RS? So reference value and decrease 10 megaparsec.
yeah,
So how much percent of the
yeah. So do you remember the values of H naught that we talked about?
Sorry.
Yeah, so those two values. If I reduce RS by 10 megaparsec, the value inferred on the direct detection go exactly to this value.
before decreasing the reference value?
Yeah.
What is the value of RS reference value?
Oh, exactly the value of RS.
Yeah.
That should be, I don't know by heart, but I can check for you. I don't remember.
Yeah.
It is something like 147 megaparsec.
Then which means that about
10%.
10%.
Yes,
Below 10%,
Yeah.
about 7%.
exactly. Yeah. Exactly. That's exactly. So it is something like less than 10% change that is necessary. Oh, thank you. So, okay, that's what it was. Yeah, so we need a change of around or less than 10% on the value of RS. And you might think that's not a lot, right? 10%. With the precision of the data we have nowadays, that is really getting us this cosmological parameters with a lot of precision. It's very hard. The data is very resistant to changes in the cosmological model. So we're having a lot of trouble. Yeah. So the last way of change and changing recombination, people had a few ideas like including the effect of primordial magnetic fields in this, or even changing the electron mass Yeah, I swear, who are doing this. So they say, oh, at late or early times, the electron mass was different, and today it has the value it has. And actually, if you forget why you're doing this, if you forget the physics, if you only think of phenomenology, this type of thing really performs really well in solving the Hubble tension. So there was this paper called the H0 Olympics. It came during the Olympics, so that's why they were very smart. And they gave medals to the models that solved the Hubble tension better. And for my surprise, varying the electron mass, it is the first time. It really solved the Hubble tension. So I think they put like a step function on like, it is the value today is 1, and then the value of it is a different at early times, and compute everything with that. And again, this is phenomenology, and I'm going to explain why we need to do such crude phenomenology for this. It is not so crazy, I know, it really shocked me, but it's not so crazy. Yeah, please.
Is the changing of the electron mass due to the renormalization?
No. You could actually, okay, that's a good opportunity. We have a bunch of theories. Find a way of doing this. Go see their paper, see exactly what type of electron mass change they have, and tell me if this is possible for any theory. That's what is missing in this field, and that's why we need to talk more, all of us. And I'm going to say why people are doing this type of phenomenology, which seems like, oh, right, oh, that's a bit too much, but I'm going to show you why this is so important.
Here, omega k, is it open or closed?
Oh, I don't remember. Yeah, but you have to vary. Yeah. It cannot be flat. I think it's closed, from what I remember. Yeah. But I don't quote me on that.
Is it possible to consider that electron mass is what it is, but add another particle with whatever pairing mass they want?
Yeah, so this is what people tried here. So this would come in this category. So I'm adding a new particle that has a different dynamics. So this would change the entire dynamics of that theory. So people tried a few things. They said, oh, let's have some light relics. Let's have a new dark energy component. People even said, okay, let's couple things to the neutrino, because this is exactly the time where the neutrino becomes non-relativistic. So there is like an increase of energy coming from the neutrino in that. And this is one of the models that people have proposed. So indeed, it requires some physics. Like you have to think with which type of physics can be happening here that could be changed to solve this.
Was there any issue when they added new particles?
Yeah, so there's no issue. It just, when you do the data analysis, the data tells you you cannot have as much as you need of them. You can have, but they don't solve the problem, because there's other things that change if you have them. Let's go back. So primordial magnetic fields here gets bronze metal, and other models get silver. And this is the model we're going to talk about today, which is called early dark energy. So dark energy is the component, it is the name we give to the component, whatever it is, that explains the acceleration of the universe today. We have no idea what it is. So we give this fantasy name of dark energy to whatever theory I can have that can explain the late time acceleration of the universe. So it is something that have an equation of state equals to -1 or smaller than -1/3. What if, just for a short period of time in the early universe, I had dark energy there, enough to just stretch this RS, enough to solve the Hubble tension? So this idea, it is the early dark energy, and we're going to talk about it. Let me just pause here a little bit to say something that I had to learn in this field. So when I entered this field, being a theoretical physicist, high energy background, I was like, these people are crazy. Phenomenology like this is crazy. No. I've been humbled by this, because it is so hard to solve this tension that if you come and you construct the best first principle model and you do 3 years of work, you get there, you analyze with the data, it doesn't solve, because it doesn't allow to have that quantity, the data. So people are doing this type of crazy out of the hand phenomenology to solve the Hubble tension because it's hard. We need first to understand what is the mechanism that works. And then when we find a mechanism that works, we go back and find the UV theory to explain this. So but you can have your own opinion, but I did not like it. But I was humbled by it after I entered the field, started coming up with my own models and doing the data analysis, and nothing works. So that's what I mean that theories are behind in this sense, because the truth is, those are good explanations, but not that good, right? We need to do better. This tension is here, and we don't have a good explanation that has a good physics. So this is just my personal opinion. I was really humbled by this. Yeah, okay, so let's talk about early dark energy. Yeah.
So I'm going to explain the sigma tension also.
What?
Sigma.
Yes, I will.
Actually, because Hubble tension could be solved. There are several there to solve this one. Probably you can solve some of the other tension.
Yeah, I'm going to talk about that. And also, let's use the word solve very carefully, and you're going to see why. As you might understand from the title of my talk, there are statistical problems in this that may lead you to the wrong conclusion if it is solved or not. The Hubble tension. So it's not like we have a lot of models that solve. We have very little models that may be solved, and most of them don't have a theoretical explanation. They're just completely phenomenology. So, and the SA tension, it is dying. So it's not there anymore. So, okay. I'm telling you, I'm here to any observational thing you've found in the past few years, you can ask me, because that's what I did. Okay, early dark energy. So what is the idea? The idea is that I add an extra component to my lambda CDM model, which with the goal of increasing h of z, right? But I'm only modifying the early universe. So this needs to, this needs to act around matter and radiation equality. Remember, so timeline of the universe, right? We don't know what happened in the beginning. We have here radiation period, we have here matter period, and we have here dark energy period. Oh, what? Oh, there's me. Oh, thank you. Okay, so dark energy.
Oh,
Here's time, here's radiation. We don't know what happened in the beginning, right? And here's the dark energy period. And here's today. And we're talking about things, this recombination where the photons streaming are here. So here is what we call the last scattering surface. Equality between radiation and matter is here, right? So I need a component that behaves like dark energy, so behaves like this guy here, but it's not this guy, cannot be the same, doesn't work. It's just another thing that starts behaving around matter radiation equality here, starts acting and dies, because we cannot have it today.
So you cannot modify before and after.
What's our,
You cannot modify before and after. So it's
you could have something that was a little bit more long-lived here. So you have less.
without touching the Big Bang procedure.
Yeah, but then, yeah, so BBN is here, you cannot touch that. Yeah,
So you have a boundary below and above.
you do, yeah. So it is a really terminological idea, right? Like, let me just put like, whoop, something there to do what I want to do. But let's see if this works. And from what you saw, this is one of the best solutions, if not the best solution, I think. Oh, I went too far. Sorry. Okay, so this is the idea. And when I say it has to dilute faster than matter, I mean that it has to decay really quick. Because what happens? I want to have this component I want to have as much as possible. So I want to have like 10% of it, right? Because I want 10% change in this. So I need 10% of this component. But then it has to decay. So it has to decay really fast here, so I can have the maximum height possible. I know, it's phenomenal. It's how do I do that? What physicists use to do things? Taylor fields, right? Taylor fields to the rescue. So here, let's add a scalar field. Here, I put a pseudo-scalar field because we can actually test other things. In a Friedman-Hobson-Walker background. So H here is the Hubble parameter, and here's the potential. So as you can already imagine, I need to find a potential that makes this start acting and decay fast enough, and also give me the biggest height possible. We have a canonical EDE, or a toy model of EDE, which is this type of potential here. So this is an axion-like potential, right? We see those in axions and axion-like particles. But we allow this to go to some power of n. And again, the idea is that this is going to behave like dark energy depending on the potential. So I have to choose this potential well, so this behaves like dark energy. So the canonical ED model, it is this one. It is the most studied because it is the one that gives the biggest resolution to the Hubble tension. And here we can see, so what are the parameters of these models? We have three parameters, right? So we have the mass of this field. It has to be ultralight, so it has to behave like dark energy. We have to have a certain value of the spontaneous symmetry breaking scale, and n controls this decay. And we have the initial value of the field. You can also think about this in what we call phenomenological parameters. After all, we're doing phenomenology, right? So we care about how much of this I have. So we recast those particle physics parameters into FEDE, which is the fraction of EDE. So when I say I need a 10% of EDE, this means I have something like a 10% fraction. So here I have a fraction of EDE, here I have the redshift. And this fraction of EDE, I want the fraction at ZC, which is the redshift where it's maximum. Right, so this is my second parameter, ZC. The redshift where it's maximum. And then I have the initial value of the field, and I have n. N is going to control how fast this decays. So this is early times, this is late times. So I need a component that grows fast, and then it decays fast.
Numerically, what is n? Okay.
Yeah. So here are, so you can see how fast or how much these parameters influence how fast it decays. We usually fix n equals 3 because it is what solves the tension better. And why does it solve the tension better? Because it decays faster. So it allows you to go higher and decays faster. But I challenge you to create a potential of 1 minus cosine of pi to the third power. With n equals 1, axion-like, easy, we all know how to do it.
But the evolution of phi, what is the relation between phi and f? So
yeah, you have to have a
X
theory
or
for
you
that.
can write an expansion.
Yeah, you have to have a theory for it.
So in other words, okay, what about the boundary conditions? The initial boundary, you have to tune them.
No, we don't go there here.
You have an
Yeah,
evolution.
you have the initial value. That is the only thing.
Yeah, so
And you know how much
sensitive to that initial value.
it is a bit sensitive, yes. Yeah, it is sensitive to ZC and is sensitive to the initial value. So that's why when I wrote this, I didn't write a fat tail for 30 times because I know this doesn't work. And again, why? Data.
Anyway, so you need something that opens up and then closes. So, I mean,
Yeah.
it's self-contained.
Exactly.
So
So it's tough because you need this third power potential. That's very hard.
but the initial value is
And then
high,
it's-
the field is
Yeah, so it is high, but it's not as high. It's not in the top of the potential. It's some sort of in the middle. It's not on the top of the sorry here. So it's some sort of in the middle.
happens earlier in the universe. It just stays there.
It just stays there. Yeah. And then it's frozen, so it's behaving like dark energy, and then it starts decaying and then stops. That's where the oscillations
But then you
come.
have a dark
right?
energy also before at radiation time.
Yeah, that's why this has to be some value where this dark energy at early times is low. You cannot have.
You cannot affect the
Yeah.
PM or anything.
Yeah.
So it has to be very
So this
small.
initial value needs to be something that when this field is frozen, it doesn't affect too much.
It's frozen for very small value,
Very small
extremely
value.
small value.
Yeah, and for some reason it
frozen
does.
very late, it moves a little bit,
Yes.
and that's it.
Exactly.
And what about the spectrum of the BBN and everything? So so once you have this, you add this additional ingredient.
Yeah.
So
So if
to affect also how you analyze.
Yeah, so you can put that also in the analysis, right? You can put a BBN bound in the analysis, and then you know how much this initial value can be, for example. All of this is taken into account. So there's a lot of challenging for theories, right? Why this potential is extremely fine-tuned, extremely, to this shape. It is extremely fine-tuned to n equals 3. The initial condition has to be really fine-tuned also to be something that leads to a stop fraction. It has to go up in the right time and decays. But it is currently the best solution for the Hubble tension. So that's why I say it humbled me. Because even when you come with a very fake model, in some sense, right, a very homological model, it's still really hard to solve. And I can tell you, we tested many potentials here. Polynomials, inverted polynomials, exponentials, everything, nothing solves as well as this with n equals 3. And even this with n equals 3, we're asking ourselves if this solve or not.
It's a good thing. Because we kind of constrain on what model works. Otherwise, we have
Yeah.
too many models that everyone work for inflation. Now,
You're right.
realistic number of models that work.
I think that's a positive way of seeing, because for dark energy and for inflation, the zoo is, I usually when I give my dark matter talk or my inflation talk, when I put the models, I put state of the art. Because what is a state of the art with orders of magnitude in the possibility of models, right? And we are all competent enough of a theorist to, oh, this doesn't work out, then let's add this term here. Let's add this interaction, let's add this extra component here. And we solve the model, right? You're right, in this sense, this is good because it's not taking our bullshit as theorists, right? No, this is hard to solve, yeah.
Here's something to prove to remain the potential. You show the example.
Yeah.
About it. You show the mechanism.
Yeah.
So mechanism is already known.
Yeah.
Already known. And you show the example to represent the mechanism.
Yeah, exactly. Yeah. But the problem is that it's not just a mechanism. It's not like early dark energy works. No. Early dark energy with this potential and very specific values for those works. Yeah. Which is the complication here. So there's a huge fine-tuning on that. And then we did all of this gymnastics, right? We took our theorists' jacket off to be able to say, okay, I'll do some phenomenology. But it's better solve the Hubble tension, right? Because I risked everything here. My reputation as someone that knows what it is doing to make this is better. Great. 2019, this group of people went, and very good people that do data analysis, and analyzed this with Planck data, which is CMB data, plus large-scale structured data where you're seeing galaxies, and also supernova data, including the data that is in tension with the Planck data. And they got actually that if you use early dark energy instead of lambda-CDM, you get a high value of the Hubble tension. You reduce the tension to less than 1 sigma, and then you solve the Hubble tension. Great. It is a crazy model, but at least it works, right? So you need here something like a 10% of FED to solve it. We were all very happy that finally we can go to the drawing board and try to find a UV theory that explains this, right? But we also realized that when you increase H dot, because remember, we are fitting all of those cosmological parameters together. So if one changes to this side, the other one that is correlated to it is going to change it to the other side. And this is what happens. Because I have more dark energy, to do a good fit, it requires more dark matter than the cosmological model, and it requires a higher spectral index from the primordial universe than we love this idiom. So then this group came and said, oh, if you're messing up with the other cosmological parameters, you better use better measurements of these other parameters from late time to see if this other measurement allows you to do this change in the dark matter quantity. And it doesn't. It doesn't. So when you come and add more data that tells you the amount of dark matter in late times, for example, it tells you, no, you go back to 68. So early dark energy actually does not solve the Hubble tension. It is just because you did a bad data analysis, right? You did not include all the data with all the information that you have. So you still have a 3.3 sigma tension with shoes.
So when you say that you need more dark matter,
Yeah.
how much?
I think I have a table. I have a table, just slightly, yeah. So then they did another analysis with more data and they found the same thing. So when you don't only use Planck data and when you use also information that you have from those galaxy surveys about what is the amount of matter that you have nowadays, this doesn't allow you to increase dark matter as much, or S8. Dark matter means S8 as well.
So what is the mechanism by which, by modifying the evolution, the expansion history of the universe before radiation equality, radiation matter equality, what is the mechanism that affects very late data on structures?
Yeah. So it's all about so I changed my model. So I put this small, and then I have here the CMB, right? And when I went and measured the CMB, everything I measured in the CMB, it is going to also be propagated for later. But the CMB the CMB has some degeneracies in it, what we call dark degeneracy. So it has a degeneracy between some parameters in it. For example, dark energy cannot be measured from the CMB alone. H naught. So yeah, so you can't play around with CMB saying, oh, I increased this and I increased that and I increased that. So for example, giving a good example, the amount of matter, so this is CMB. The first peak, if I know that there is dark energy, gives you the amount of dark energy. But the amount of dark matter is also a combination of the second and third peaks. So yeah, so if I shift a little bit one of those, you might shift the position of the other. So there is a compensation you can do a little bit by increasing a little bit here, and then that you can actually compensate for those parameters. This is just a compensation of. Another way of thinking is that I have more dark energy, so I have more of a component that doesn't allow the universe to evolve in the way of matter. I was supposed to have only matter at this period.
So that's why you need a little bit more.
Exactly. But then I remove a little bit from dark
You have
matter.
the boundary conditions at that time.
Exactly.
A little bit,
And then this propagates. Yeah. Yeah. But it propagates a lot. But then we have those measurements here. So what they were doing is saying, oh, you cannot do that because this measurement here doesn't allow you. Okay, so here are the values that we wanted to see. So this quantity is the quantity of omega dark times h squared, little h squared. So it is an increase. It is an increase of, yeah, maybe 10%.
Era questo non è quello che adesso è segnalato, non era quello che avevo detto, solo che no, ma di qua.
Is there any question?
Prima perché non
I'm sorry, you make a noise.
messo già.
I don't know who.
Se lo rimettiamo c'è quella nuova formula. Solo che adesso io penso che comunque di qua si vede che questo è solo un'approssimazione.
It was a mistake. We've all done that, right? So what happens if we increase the amount of matter? This also increases this quantity that we call S8. S8 or sigma 8 is basically telling you the amount of clustering that we have. Right, so if it's dark matter clusters in a certain way, right? The evolution of the universe, things clump and clump and clump in a certain way. If I have this early dark energy, things clump in a different way. So I have a different value of this sigma 8. So this predicts a higher sigma 8, which, as we're going to see, makes the sigma 8 tension worse. Okay, so their conclusion is, main message, early dark energy does not solve. So we did all those gymnastics. We left all of our knowledge and training away for nothing, right? This was 2020. But then a lot of people started to think that maybe this is not the end of the story. And I'm going much slower than I was planning, so sorry. Do I still have maybe 10 minutes?
Yeah.
Okay. So when we see those contours, and remember, I showed you contours that were super cute, right? They were like, and they were like that. So this means this thing was constrained. This value here is between this value and this value, and this value is between this value and this value. When we started looking at the constraints of these people, there were these huge blobs, which means that those parameters are not constrained. So the data is not powerful enough to constrain those parameters. So, like you said, if my theory is sensitive to changes of this value, the fact that this value could be very spread out could be affecting my value of FED. So for example, statistically, the way that the Bayesian analysis works is that you have a higher volume here, right? Because you have this little thing. So your mean of your result is going to be here. But this doesn't mean that this is where the result is. Everything around here is equally good 1 sigma. So the truth could be here. But because here you have a higher volume for some statistical reason, you are stuck there. And then this is going to give you a wrong result. And this is going to propagate to the other quantities. Because each of those contours, so this 1D here contour, it is the projection in 1D of these quantities. So if I'm projecting something that was not constrained, so this is only statistical fluke. And I project and I reach a conclusion out of it. For example, here, I'm projecting, oh, here's my peak, right? This is the answer. This is not your peak. This is some statistical fluke.
Because there is a much volume in the
Exactly.
other direction.
Much
It's
exactly.
simply that.
Yeah, exactly. And why do you have more volume? Because you just maybe got stuck there or something.
Question. In order to have volume, you need to parameterize your model. I mean, you have to for instance, if you analyze the data on a logarithmic or linear scale, this will change things.
It can change in some analysis, not in this.
Not in this.
This one is very resistant to that. Yeah. So yeah, exactly. So what we're seeing here is what we call volume effects or prior volume effects or marginalization effects. There's many different names. which basically means that you're projecting and then whatever has the higher volume gets preference, but that's not necessarily where your data is. In the case of ED, it's even worse because the way we parameterize the model.
No, but what are the priors? The point is the prior.
Yeah, so here in this case specifically, this is a prior question for sure. When
But
prior
in
volume
Bayesian
effects,
analysis, priors
when
are
prior volume effects are present, doesn't matter which prior you put. You're going to have the problem. Unless the problem is not there, then the priors matter. Your analysis is better or worse. So if you have a prior volume effect that's it's solved with just changing the priors, this is not a real prior volume effect. It's just like you needed to figure out what is the best prior for your data analysis.
But in a Bayesian, the problem of a Bayesian analysis is that you start with a prior, you add some data, and you improve your knowledge. However, the improvement is multiplicative. That means that if your starting knowledge is zero, whatever you do times zero remains zero. In other words, your prior need to be so robust. Otherwise, all the Bayesian analysis is completely useless.
I agree. It doesn't exist non-informative priors, like people say. I agree. But in the limit of infinite data or enough data, everything goes like away. Yeah, it is not. Right. So
What is the volume?
what? Sorry.
What is the volume?
Volume. I mean this, right? Because here it has higher volume than this. So when I project the higher volume region, it's going to be preferred, but that's not necessarily where it is, because the higher volume region was there just because you couldn't constrain this at all.
Because they use a Markov chain, so basically the Markov chain remains stuck in some region and continuously goes around and round and round.
So in the case of FED, that's true. It is terrible. FD is what we call a nested model. So it has a lambda CDM limit. So when FED is zero, it doesn't matter the value of those two. So when FED is zero here, those two don't matter anymore, right? So then it gets stuck there because they don't matter. And then, so is this true? Is it true that FED is close to zero? Or is this just preferred because statistically I'm going to always prefer a model that has only one parameter instead of three? So basically that is, for example, what happens here in quadratic matter. So yeah, this is what prior volume effect is. So when you have large parameter regions, they are emphasizing compared to smaller parameter regions. And this is only coming from the statistical analysis. Again, as you pointed out perfectly, this is an inescapable feature of Bayesian statistics. Bayesian statistics, you get the likelihood times the prior, and that is how you do the analysis. Then you get your posterior. So all of those things we saw, we call posteriors, right? Your data is the likelihood times the prior. And priors are good. If I have a theory that cannot have a positivity bound, I put a prior. It cannot be, neutrino mass cannot be negative. I put a prior. Priors are actually good. Priors are your knowledge, right, of something about that theory. But priors can also be dangerous and can cause this type of. So we need to be careful about that. Just a cute example of prior volume effect. So let's say I have experiment 1 that measured this black contour here, right? So the black contour has this really weird non-Gaussian feature here. But since the volume here is bigger, my preferred value for this model for parameter alpha is going to be here. And then let's say I measure experiment 2 that is only sensitive to parameter alpha. And then it finds it here, because that is actually the right value of alpha. So those two are going to be in tension, those two experiments, like the Hubble tension. Why? Because my Bayesian analysis was flawed here in this way, right? It has this volume effect that you have to take into consideration. You have to look at your contour and say, there is a prior volume effect here. And I'm going super slow, I'm so sorry. So when prior volume effects appear, when my model has more parameters than the data is capable of constraining. So that's why I want to give this talk to theorists, because I was the same. I wanted to do my model because I had a good reason for that model, but that model has 5 parameters, extra parameters. You cannot constrain them. That's why they do W0WA parameterization for dark energy, because that's what it can do. We can mostly constrain with the data we have now, the 2 extra parameters from lambda CM. 3 already gives you this. So we have to be careful when we do our models. Our models can be better for many theoretical reasons, but if they have 5 extra parameters, 4 extra parameters, they're not testable. The data cannot say. When the posterior is very Gaussian, like our example, we saw, when you have the parameters structured like the one of FED, which is nested. So those things appear. And this can then bias your marginalized posterior in the parameter that you wanted, which is H0. So the value of H0 that they got is not the true value of H0, it's a biased value of H0. So here is what we were talking about for those that don't do. So the cosmological analysis are Bayesian analysis, right? So basically, we compute the posterior, which is the likelihood times the prior. Prior is our prior knowledge, something we say about the data. So those effects always appear in Bayesian analysis, right? Okay, just saying this appears also for the neutrino mass. The sum of neutrino mass also suffers from prior volume effects, or even prior. If you change the prior, you completely change the result of your analysis. And also the tensor to scalar ratio R, which is something we're looking for the future too. Okay, so what did we propose when we saw this in 2020? The cosmology community didn't know what to do. One say it is, the other say it isn't. What is the so we proposed to use actually a frequentist method. Let's go back. We've been using Bayesian, but particle physicists use a lot of frequentism, which is basically working with the likelihood and not using the prior. And we computed what we call a profile likelihood, which is something like a likelihood. Basically, the profile likelihood, I think the next slide is a little bit better. So this is a profile likelihood. So here is delta chi-square. Delta chi-square, it is just the same as the likelihood. So I fix one point of the quantity I want, let's say H0, or here the amount of variance. And I minimize my likelihood with respect to all the other parameters. And I do that for many points. And then I get this type of thing. The bottom is exactly the value of your parameter that you want. And then you get the confidence interval by saying where this overlaps with 1. Why is this good? At least it doesn't depend on priors. I'm not saying it's good or not. Probably it's going to give a worse result because you don't have a prior to fix things to small value. But if the prior is the culprit of what is happening, here's going to give you a different result from the Bayesian analysis. So that's what we did for early dark energy. So we computed the profile likelihood for the FED parameter. And those are the profiles that we got, right? So we saw that actually for when we do Planck plus Boss, we can actually have almost 9% of early dark energy, where the previous people said it has to be smaller than 5%. That's why it did not solve the Hubble tension. Putting more in a better way. So here now we have H0, I think it's easier to see. In pink, we have the Planck value for lambda CDM. In gray, we have the Schultz value. So closer to the Schultz value, the better. So we can see here that now our profile likelihoods really are closer to the Schultz value. So it tells us that ED actually, it is 1.4 sigma away from the Schultz value. So actually ED solves the Hubble tension. What we were seeing before, that we're seeing very low values of H0, it was just prior volume effects. Here is just more. So we saw that the ED can be solved by the Hubble tension can be solved by ED. So we did this with profile likelihood, and there's many codes now. So we were the first ones. No one was doing this. We brought this from particle physics, and the cosmological community. It looked like we were showing them something that they never saw in their lives, and this is just frequentist statistics. Oh, I know. They are okay with machine learning, but they are not okay with frequentist. But I can say that with the years, this changed, and now big collaborations use this. And what about the assay tension? So the assay tension is this tension in this clustering parameter that we have, which is also like, depending on the way you measure this, you get different values. But this is a much milder tension on the order of 2%, of 2 sigma, sorry. And as we saw, EDE worsens that. So here we have, for example, H0, S8. Again, those are the values that we measure from Planck and from the S8 from Planck, the highlighted regions. And as you increase FEDE, you go farther and farther away from the S8 region that is wanted. So to solve the Hubble tension, you need here something like 10% of ED, 9%. This, then it's far away from the S8 tension. So the ED model indeed makes the S8 tension worse. So if this is the solution to the Hubble tension, this makes the S8 tension worse. I don't have time, but just really quickly, what we are discovering, and I have a paper coming out on that, is that it is also volume effect, the S8 tension. So there was never an S8 tension. It was just because they had all those nuisance parameters that we talked about, right? Those 40 things, unconstrained. And those were actually affecting the S8. And actually the collaborations agreed with us. So KIPS collaboration and DES collaboration already also don't think that the S8 tension exists. So the S8 tension is falling. So we don't think this exists anymore. But this is not the full story. This was 2022. We now have the new ACT result. Again, a Bayesian analysis, and they claim ED doesn't solve. You cannot have enough ED. And this is new CMB data. But then some people came and do profile likelihood and said again, no, it can't. Was just volume effect. So this keeps going. This keeps going. SPT data, same thing. So the conclusion for me today is we don't know. We are again in the same region. We don't know if ED solves the Hubble tension or not. So although we have better data, although this data is more precise, although we're getting better in statistics and all, we still don't know what solves the Hubble tension. So just wanted to say the prior volume effects appear everywhere. So if you're doing neutrino mass analysis or S8 analysis and everything, be careful. The entire DESI result for W0 WA done with full shape, it is dominated by volume effects, and they don't even quote in the paper. So now the big collaborations are aware of that, finally. So they are not even quoting the results that are dominated by prior volume effects. So then you have to do this type of analysis or something else. So I leave you with my conclusions since I don't have more time. And sorry that I went over time, and thank you so much.
Thank you for giving the nice shot. Do you have any questions?
About the frequency approach.
Yes.
As I know, the frequency approach was hard to analyze because there are not a lot of data can analyze in these frequency approach. You can do it in the way.
Yeah. So I think it is a confusion of people that Bayesian analysis doesn't suffer from that as well. So it is just what is the interpretation of the confidence interval that it gives, like this 1 or 2 sigma away, right? In Bayesian and in frequentist, what it means. So when you only have one realization of the universe, we actually exchange this by saying that we have many patches of the universe that we can actually, a lot of data. So we kind of trade the fact that I don't have many experiments to the fact that I have a lot of data from different patches and they all agree in some sense. But this is valid for Bayesian and for frequentist. You just have to interpret the frequentist in a better way. It's not like how many times I roll my dice, and it is what is the chance of that result be within the true value. So that is what my contour is saying for a frequentist analysis. So it is still a frequentist way, but it's not in like repeated experiments. But this is also valid for Bayesian. It is the same problem. It is just because we know frequentist better in this way, right? Throwing a dice 10 times, yeah.
So it does mean that you analyze the universe as many universes.
No. Like it doesn't mean in the Bayesian analysis that I analyze the universe in many different ways. After all, I'm also using a likelihood for Bayesian in the same way, right? So that is the way that cosmology has to go around the fact that we only have one universe. Yeah.
So let's say what you said is that the ACT data makes it harder for the EDE model to work.
Exactly. The ACT data does a Bayesian analysis and actually says that this is the H naught values you have. This is act, and this is Planck plus act. Look how low it is, only act. It is not even 68 to 67.
Mm-hmm.
So act alone gives a very low H naught value. And yeah, and we kind of understand why this. So act doesn't have the first peak information, so you actually have a better measurement of H naught. Yeah, so this means that you don't solve the Hubble tension if you take into consideration act data. But as they say in this paper, but this was a Bayesian analysis. If you do the frequentist analysis, and this is the blue is frequentist, and the red is Bayesian, you see that you shift the value, and it's now in agreement with shoes. So it is still a statistical. And you can see that not everybody agrees with that, right? Otherwise, the act team would have said, oh, there is volume effect here, but they
또 question?
So with all this subtle volume effect, does you still the DESI data show that lambda is not constant? And
Okay, so DESI data measures, there's two DESI data analysis. There is the PAO data. So here we have the power spectrum, and there is, right. So the PAO analysis just removes this and just analyzes this. This is the PAO analysis. The PAO analysis for DESI data doesn't suffer from bottom effects. And this gives you the hint for dynamical architecture. There's another analysis that they call the full shape analysis, where they actually try to fit the shape of the power spectrum, including the things, the entire shape. You have much more parameters that included your analysis. So you go from like 40 to 50. Those have volume effects. In the paper of the DESI of the W0, WA full shape doesn't even quote the value of W0, because it's totally dominated by volume. So people are.
but one is enough to say that lambda is enough. Okay. But that one is enough to say lambda is not.
If the chair allows me to give my second talk, I'm not going to give it away, but it was super cool. This is super cool. This is also don't trust the data talk. Let me just show you one plot. So this is the W0 WA plot from DESI. I think all of us know what we're talking about, right? If you don't, let me know. I give a short introduction. Okay, so this is what is important about DESI data. And then you decide what you think about this. And I know what I think about this, and I'm going to tell you what I think. If I do WA, W0, and I do DASI alone, BAO, which is the one that is okay. This is the contour. Remember that here is lambda's event. DASI alone doesn't tell you anything. Oh, okay, it's okay. DASI cannot constrain everything, so let's analyze it simply. Again, the contour is too big. It doesn't exclude necessarily anything. It doesn't give you a hint of dynamical dark energy. Okay, then CMB is not good. Let me put supernova. And again, you still are compatible with lambda's event. Only when you put DASI plus CMB plus supernova that blooms, this goes down. Now I ask you, do you know if those data are compatible that you can combine them? How many parameters do I have in this data analysis that leads me to this? My opinion is that it is a very good hint, very good, these people are good, but it is a hint of combined data sets. And as this talk that I couldn't give it to you, there is what we call the CMB BAO tension, which is when we compare some values of the BAO parameters from DASI and from CMB, they are 2 to 4 sigma away from each other. I think I have one slide. Yeah. So if I get the BAO parameters, which is omega matter and RDH from DASI measured those parameters directly. And I get the one that I measure, for example, from ACT here. Those things are 3.7 sigma away. ACT here 3.1 sigma away from DASI. Planck, it is 2 sigma away from DASI. Are they compatible or not? Can I combine them or not? The SBT team doesn't even put in the paper that combination with DASI because they claim that those data sets are not compatible. So could it be, and I don't know the answer to that. This is just to be provocative because this is what the data is telling us. That when I combine DASI and Planck, I'm combining data sets that are not compatible with each other. And actually the W0 WA, it is the new physics solving this tension. Could be that it is, could be that it's not. Could it be that just we have mistakes in either CMB or DASI measurement? So that was my second talk, like 5 minutes. Yeah, but that's very interesting. So this is my second, let's be careful with the data because they are just combining things that might not be compatible with each other. I'm not saying it is not compatible. I'm saying that it might not be. I plotted this, and for me, this sounds shaky. So